So we'll start our session. Welcome to the fourth installment and the last one for this session shared event. It's going to be our last one for this year, but hopefully it will not be the last one for the years to come. I hope this, let's say, trend or tradition will carry on in the next years, because we have learned quite a lot from it, and we gave people a chance to express themselves by sharing their ideas about science. In this last session, we're going to have 3 talks about. One is about cybernetics and robotics and the Uncanny Valley, and Mr. Baldacchino will be talking about it. We will have another one about animal behavior. Ms. Attard will be talking, presenting that. And then we have one about the geomagnetic field, and Timothy Debono will be presenting that.
Which is about robotics, cybernetics, and the social aspect, which was termed the Uncanny Valley. So starting off, the practical aspect, I'm just going to talk about the basic components that are used in robotics and to a certain extent in cybernetics. Starting off, that image you have there is a robotic hand holding a light bulb, and the point is to show how many things we take for granted. The simple act of holding a light bulb requires a very complex control system, which is our bodies. We need to press firmly enough that it does not slip our hand. But if we apply too much pressure, we shall break that light bulb. In fact, an interesting dissertation we had in our labs was a system that mimicked our human fingers so that it could detect slip, something that we do practically every day and take for granted. So the field of robotics is a very wide field, a lot of disciplines and a lot of work that is continuously being done. Now, from a historical point of view, as humans, we've always tried to take advantage of our environment, and we take inspiration from nature. Apparently, even the Greeks got this idea, and this particular Greek god, I can't pronounce him, but the Romans called him Vulcan of craftsmanship, who created so-called golden mechanical handmaidens that could speak with humans. So in terms of science fiction, it's quite impressive that back in Greek times they had this wish or this desire to have such automatons around them. It shows to show that as humans we've always wished to replace manual labor with such constructs. Now the word robotics originated from the Czech playwright Karel Čapek, from his play RUR, which stands for Rossum's Universal Robots. The word robot is from a Czech word that is used to mean manual labor that is of low value. So basically a robot means an artificial slave. So, of course, in the play, the robots are sentient and they are forced to do menial labor. The story goes that they revolt against their human overlords, they take over, they form, well, it's a long story. So, let's get practical. Actuators. Anything that moves requires an actuator. Our hands, our muscles, everything requires movement. So, I'll start off with conventional actuators, the simple stuff. You can have hydraulic, pneumatic, and electrical. They're split into these 3 groups, and each has its own advantages, and each has its own varying complexity. For example, on the left, it's called a gear drive. As you can tell, you have hydraulic fluid, you force it between 2 closed gears, and you obtain torque from that. And the one on the left is quite simple as well. It's called a solenoid. It's an electrical motor where you simply have 2 poles that attract each other, and the one on the middle is somewhat more complicated. It's called a rodless pneumatic cylinder, where you use magnets to transfer the torque, you have flexible seals. So actuators are the building blocks of robotics and cybernetics. And at the end of the day, what we are in fact interested in is just the torque or the force that they give us and their rotational or linear speed. The reason that hydraulic, pneumatic and electrical actuators exist is that they each have their own advantages. So for example, hydraulic actuators, they can give you very, very high amounts of torque or force since they are working with an incompressible fluid. You've got a pump that drives the hydraulic fluid and you've got the actuator. The disadvantage in this case is that since you're working with a fluid, you've got inertia. You first have to induce movement of the fluid and then you get movement of the actuator. So their response time is, or their response behavior is pretty paltry. On the other hand, you have pneumatic actuators. They rely on compressed air, which compared to hydraulic fluid, inertia is much less of an issue. They have very, very fast response times, but then again, since air is compressible, you can't expect a lot of force from them. Another side benefit is air is free. I mean, it's all around us. All you need to do is compress it, so that keeps costs down. In fact, it's the major prime mover in the industry. And in between, you have electrical motors. They provide a good balance between torque and speed, but they are in fact taking over from what hydraulic and pneumatic used to do thanks to modern day control. So really, if in the near future you were to meet a robot or a cyborg, his hands will be all powered electrically. It's a no-brainer really. Let's go a little bit unconventional. Here we have so-called shape memory alloy motors. I guess most of you have heard of so-called shape memory alloys. They're a particular group of alloys that make use of nickel and chromium and all manner of elements, and they are passed through a specific heat treatment. What this means is that you have a metal that you can bend it, and if you apply temp heat to it, it will return to its original form. One artistic use of such alloys is, for example, you have a light fixture with a frame around it. You turn on the light bulb, and the fixture starts to heat up, and the frame will gradually open up. In this case, it's being used to power this little robot. It's called the Roach, which the makers claim is the smallest untethered leg robot to date. If anyone happens to have a penny, you'll know with the size, and in terms of weight, this little robot just weighs 2.5 grams. So it shows us how they are being used in a practical point of view. Another interesting interesting means of getting actuation are so-called electroactive polymers. They work they work in a way that you have a polymer with ions that they are not locked by dislocations. So the outside of the polymer has a conductive coating applied to it. If you apply a potential, it causes the ions to move to one side of the polymer and basically have movement. The main advantage of these polymers is that you can get a very high power to weight ratio. In fact, one of the things that they were playing for us are so-called bird planes, where you have basically a layer of photovoltaic material, a layer of lithium polymer battery, and then the actuator itself. So this company envisions whole flocks of these birds flying around, thanks to this actuator's high power to weight ratio. So let's move away from simple robotics and talk a bit about cybernetics. From a strict point of view, it simply relates to communications and control systems between the interaction of living and non-living organisms. And I'll talk some of the issues present. So firstly, let's say you have an implant inside of you and it fails. Unlike your car where you can open the hood, no one really enjoys undergoing surgery. So it highlights how resilient that implant has to be to failure. Another issue is degradation of that implant. The human body is a very harsh environment to live in, from the physical, chemical, and also from our own immune system. And also rejection from surrounding tissues. You cannot simply implant any material into the human body. It has to be firstly biocompatible and also non-toxic, obviously. You don't want to kill your patient. And here we have basically the three major phenomena by which things degrade. from a mechanical point of view, we have so-called physical phenomena, things such as fatigue, wear, and creep. On the right, the chemical phenomena such as aqueous corrosion and all manner of reactions. And on the lower level, you have breakdown by organics. Basically, an implant has to deal with all three acting together. And you can get combinations of these. Like, for example, if you have stress and corrosive materials, you get so-called stress corrosion cracking, where that stress leads to corrosion, corrosion leads to more stress, and you get this vicious cycle. So it requires a lot of in-depth knowledge. Here's some interesting work being carried out. Here's Professor Kevin Warwick. He's quite knowledgeable in his field. He has done a lot of work on himself in particular. In one case, he's had electrodes fired into his nerve endings, by which he was able to control that robotic arm, that wheelchair. And in another interesting twist, he had other people control his arms. So in that way, he turned himself into a human proxy. Another interesting project of theirs is basically a robot that is controlled by a rat's brain. The brain isn't in the cart. They basically took the poor rat's brain, they took a few neurons, they stuck them in a jar, they stuck it to a control system, and they interface together via Bluetooth. So quite and in reality, this is the first robotic system that uses an organic neural network. The neurons die out after a few months and they are replaced. And they notice that every new rat brain they use, the little robot has its own personality to it. So another strange aspect of robotics, which leads us to the so-called Uncanny Valley. One great pioneers of robotics is one called Dr. Masahiro Mori, who basically states that as we advance robots and they become more human-like, we reach a point where they start to infringe on what we feel is real. So for example, that little robot on the right is cute, although it doesn't look anything like us. The one on the left and the one on top of it, you start to get a sort of feeling of fear. I wouldn't want to meet any of those in a parking lot, really. So it's quite an odd subject, and it follows as such. You start with, so let's say the graph on the y-axis is how familiar we feel to it, how comfortable we feel to it, or our impact to it, and the x-axis is the human likeness, how close it resembles us. Starting off with industrial robots, to simplify programming, their axis of movement is similar to us humans. They rotate about their waist, they have a shoulder joint, they have an elbow joint, and their end effector rotates in the same way as us humans. Seeing a robot work, you start to see it as a sort of worker, but there is no connection. Another one are those humanoid robots for Puma, Honda. I guess you've all seen a commercial. They look cute, though. And then you start to go down the valley, where really you start to feel like you're looking at a zombie, or a corpse, or a living corpse. And in fact, as you go up, you reach basically into our healthy domain. Now the question is that this professor stated is, should we strive to advance robotics in terms of likelihood and actually replace us? He felt that as humans we should respect our own uniqueness and treat robots as a separate entity. That we should not basically try to, how should I say this, try to reinvent human beings, but respect ourselves and to simply let science do its thing. This is basically it. Thank you for your attention.
Everyone, my name is Attard. I'm a first year student in BSc Biology and Chemistry. And tonight we shall be speaking about Animal behavior. Well, there's a question mark behind there for a reason. So, first of all, I would like to get the most basic definition that we may come across later on in the presentation, and it's ethology. In a nutshell, it's basically the study of animals in their natural habitat. So, I don't know, if I see a puma, I will go into its natural habitat, and in order to get its ethology, I will sit down and observe. Now, the presentation is mostly oriented, how do you perceive the animal, but most of all, how does the animal perceive you? So, I have a question. How do you perceive your animal? Do any of you have pets? Raise hand.
Yes.
Okay. Lower hand. Dog owners. Okay. Cat owners. No. Bird owners. Hamsters. Okay. Anything else that I've missed? Okay. Cattle or horses. Horses. Well, I have cows too. So, now, how do you think? How do you perceive your animal when you look down or look up or I don't know, stroke it or something? How do you perceive your animal? I need you to speak now. Yes,
It's not intelligent.
Why not?
Because certain things that it does are very, very repetitive, and it's like a machine.
Okay.
You input information in it.
It's not a robot.
No, it's
What are this?
almost a brain.
They have a roach, maybe.
So it's almost like they're sophisticated parasites, as in pets are sophisticated. Because you just give them food and they give you happiness.
Yes, you basically give them food and they give you care. Anyone else? Yes.
They have their own character, each animal.
Okay, that's a very important thing. Yes, every animal has their own personality, basically. Now, I have, it's kind of off topic, but have you ever been scared of approaching any kind of animal? I'm not talking about the wildlife here, I'm trying to keep it domestic. Yeah. Okay, no, it's true. I have a friend of mine who is scared of cows because she can't understand where they're looking. She's creeped out by them, basically. Now, I have another one. How does the animal perceive you and the world? Now, how do you think that your dog, cat, budgie, hamster, fish, and horse, and cow looks at you? Or do you think that they have the higher intelligence? I'm asking. Anyone else but Brian and
Pain in the ass that feeds me?
Okay, I guess.
I don't think they all perceive the human being. I don't think fish actually perceive.
Alright. To be honest, I haven't I haven't done any kind of research about fish. I focused mainly on cattle and dogs and cats, but any other ideas?
I think they do realize who you are. I mean, as in, my parrot knows who I am.
Okay.
No,
Well, yeah,
it is intelligent anyways.
Using Christina, you're the pain in the ass who feeds him. Yes?
So for example, dogs, they know you by your name, for example.
Alright.
So if you're coming home and they mention you, you go wait by the door, for example.
Okay. Okay,
So
good.
they can make that connection.
Okay, good. Now, we're kind of talking about how they see you. So, how do you think that your animal sees? I'm not talking about generally the physics of it. I'm talking about what do you think that they can actually observe? Think. Yes.
Different movements, smells, their basic senses, and
Okay.
then they apply them in this sense. It's a good thing. Good things came out of this smell. So this thing, whatever it is, gives me food or
Okay.
care. This thing is bad. Stay away from it. For example, fire.
Okay, good. Now, this is Professor Temple Grandin, who wrote this really good book. It's called Animals in Translation, and she is the woman who thinks like a cow. Now, I got my copy from the library, and I think that more people should borrow this. It's really good. Now, I basically picked just two things because of the time limit that we have, and I'm going to try to focus on sight and sound. Basically, the most important concept that Professor Grandin tried to focus on is that animals do observe. Animals see every single detail. So, if for example, I don't know, I put on a new pair of shoes, for instance, and these are brightly colored, the animal will know that they're different, and their basic instinct is to either flee or stop. So basically that is their alarm. And Professor Grandin basically is an autistic person. And she applied the concept that every autistic person tends to see in pictures. And she observed that even animals tend to see in pictures. Now, I have a video. This will come to later. It's basically from a documentary taken from the BBC. And it's mostly oriented on dogs. So I hope this thing plays. Ah, we don't have speakers, do we?
No. Wait. My sound isn't very loud, so.
Oh, it's fine. Go ahead.
One of the things that people comment on is that dogs seem to be naturally attuned to them and to sense their moods or whatever. Part of our work here is actually to look into the scientific basis of that.
The key to a dog's ability to read our emotions might lie in something we all do without knowing it.
When we express our emotions in our faces, we don't do it symmetrically. It's been shown that if you take somebody's face when they're expressing some emotion like happiness or anger or something like that, there is a difference between the left and right side.
Composite faces consisting of two right or two left sides look very different.
One of the theories is that maybe our emotions are more faithfully presented in the right side of our face, and that's the side that we tune into. When we look at a face, we have what's known as a natural left gaze bias, so you naturally look much more towards the left, i.e. the right-hand side of somebody's face.
Eye tracking software has demonstrated that when presented with a human face, we nearly always look left first. Daniel Mills wanted to find out if dogs use the same trick to read human faces.
Shifting the direction of your gaze, we thought was fairly unique to people until we started looking at dogs.
To test the theory, his team recreated this experiment with dogs. They presented a series of images showing human faces, dog faces, and inanimate objects, and recorded the direction of a dog's gaze with a video camera.
We found that dogs, when they are looking at pictures of dog faces or objects, they will look randomly on the left or the right.
But when it came to human faces, they made a remarkable discovery.
So now we have Taz looking at a human face, so first she's looking in the middle of the screen. And here is the first eye movement on the left. She's on the middle, and she's going on the left. And then the dog is gonna be even more on the left. So now this is close, and then we can see really well that this is a left gaze.
Okay, now, what do you conclude from that video? Speak up.
That perhaps dogs can also recognize which side of the face is being more representative of a human being.
Exactly, basically, that's the whole gist of this thing. What I am trying to tell you is that animals can actually get things that we think that they don't. So, for example, tiny changes in the environment, they can actually read our emotions. If you actually go on the BBC website and you look up this whole documentary, it's basically an hour long, explaining how dogs are so tuned into our everyday life, and they basically evolved with us. That it's kind of fascinating. I'll link you to it later on. Now, this is, for those of you who don't have biology, the rods basically indicate black and white, and the cones indicate color. And us humans, we have both. And most animals have both. Yes, dogs do see color. This is a myth that they don't, but they do. They just observe everything in a more dull spectrum, because they are more tuned in to the darker light. So, for example, a dog can see color. For example, Christina's Christina's scarf happens to be of a high contrast, so they will know that that color is different. Sorry. Maybe they won't see it as orange as we do, but they will know that there is a contrast. They may be more tuned into dark environments because they, this question of contrast, I'm lost for words now. Now, sound and speech. Our pets try to communicate with us by various methods. For instance, when the dog barks, they make different noises when they're distressed, when they're tense, when they know that their owner is coming. Basically, Professor Milkos, who works in the University of Hungary, I can't remember the name because it's very weird, basically has conducted a study and seen that there is such a good tune with humans and dogs. Now, basically, there was a set of people, and the study conducted was the dog owners were made to listen to different barks at different times, basically, and they were made to guess what the situation the dog was in. And the study showed that most of the time, they actually could guess what it was. Basically, this is the end of my presentation. I hope you enjoyed it. And
Timothy, and I shall be bringing a little physics into this event. So I'll be speaking about the geomagnetic field. It's basically the magnetic field that the Earth creates. Anyone has any questions, feel free to stop me during the talk, okay? So, life evolved under the presence of a number of physical factors. The most common of these are water, gravity, light. The Earth's magnetic field is one of them. Unfortunately, when biologists tend to describe the evolution of life, not much reference is made to the presence of a magnetic field. This is mainly due to the lack of data that we have. Historical data about the magnetic field started there. Prior to that date, studies of the magnetic field were mainly due to improve navigational purposes. But that's the day that actually people got interested on why the geomagnetic field is there. However, it is unlikely that we are unaffected by it. So, first of all, behold the electromagnetic spectrum. I trust that many of you are familiar with this. Basically, we have visible light in the middle, the part that we can see, and the most high energy radiation, which is gamma. The sun sends radiation from infrared to ultraviolet radiation. Visible light is in the middle. However, on rare occasions it does emit X-rays and gamma rays during the intense solar flares, and there you can see solar flares pretty big when compared to the Earth. They travel at the speed of light, which is approximately that in a vacuum, and as a result radiation reaches Earth in 8 minutes. However, I said that the sun emits gamma during solar flares. However, the sun has a high amount of gamma radiation in its core. Gamma photons begin their long journey to the surface of the sun, during which they are absorbed by solar plasma and re-emitted at lower frequencies. By the time they get to the surface, they're pretty much within the range of infrared and ultraviolet. This is what the sun spits at us, and we need a good defense mechanism in order to be able to live. Behold the geomagnetic field. Okay, it refers to the magnetic field generated from the core. Basically, we know that a large amount of molten liquid is present in the core, and due to their high ionizing properties, and because of the Earth's thermal movement, they act like a dynamo and create the magnetic field. Scientists in the University of Maryland were actually able to replicate this in a huge room, and they've made 2 iron cores rotating opposite of each other, and they were actually able to create a perfect magnetic field. One can assume that the magnetic field is joined by magnetic field lines, which is the property of any bar magnet, which joins the north and south poles. In this way, we can visualize how this is what protects us from radiation. Looks like something the Power Rangers would build. So, electrically charged particles, which form solar wind, stream towards our planet. And due to the sun's huge size, it wraps around our field, flattening it on one side, stretching it on the other side, giving it a teardrop shape. Basically, this is what protects us from harmful radiation, and life evolved under this protective barrier. But did this magnetic field ever change? Is it constant? In reality, it did change many, many times during the Earth's lifespan. In fact, two scientists, Glasmeyer and Roberts, showed that during certain times the amplitude of the magnetic field diminished to 0. There were times that the Earth had no magnetic field, and then the amplitude of the field reversed in the opposite direction. And as we can see, nowadays we have a North Pole, which is at the South Pole, and the South Pole, which is at the North Pole. They were able to do this using a very accurate and revolutionary numerical model. It was the first model that was able to show magnetic field reversal, and it was very accurate in terms of showing also the magnitude of the magnetic field. So I have here a video, but for some reason it's not working. Her video worked, I don't know why mine isn't.
Because there was a dog in it.
So basically, that's the surface of the Earth, that's the surface of the outer core. I would like to pay attention more to the top one, because that's the one that affects our everyday life. The red part indicates the magnetic field lines coming out of the surface, blue part, magnetic field lines going in. And the darker the color, the more powerful the magnetic field. As you can see, the field in the core is much more complicated, so pay attention to the one at the surface. So we're starting to see fluctuations within the polarity. And we are beginning to see the reversal take its shape. And surprise, surprise, there it is.
So what's the time span involved?
On average, it's about 400,000 years. It takes a long time. Okay. So, the magnetosphere. The magnetosphere is not just the magnetic field, but it also involves the ozone layer and electrons and ions from the ionosphere. All of these are contained by the electromagnetic field, which is much stronger than gravity. As we know, the ozone layer does block some UV radiation, which manages to penetrate the magnetic field. As I've already mentioned, it has a teardrop shape because of the way the sun hits us. Electrically charged particles move along the field lines, and in fact, some particles do actually penetrate and arrive to the lower levels of the atmosphere. They react with gases from our atmosphere, and when such things happen, we see auroras. This happens where the magnetic field is up, when the Earth's magnetic field is weaker in the regions of the pole, like Iceland. So, will the geomagnetic field be with us forever? We don't know. We can only form an intelligent guess. Based on data over the last 150 years, scientists have been noticing a decay rate within the strength of the magnetic field, and they fear that if it continues to follow this trend, it might disappear in 1500 years. And that's bad. Why? We try to answer this question by comparing ourselves to Mars. Mars is kind of very similar to Earth. It has almost the same size, almost the same atmospheric composition. Mars to date has no magnetic field. The Mars Global Surveyor was sent, one of its purposes was to track if it has any magnetic field, and it found that it has isolated magnetic fields at different regions. It is not a uniform geomagnetic field, and as a result it does not protect against the sun's radiation. As a result, that is the surface of Mars. Its atmosphere was stripped off and oceans were vaporized by the high energy radiation of the sun. Scientists fear that this is what the surface of Earth might look like if that happens to Earth, and we think that this is already happening. This is due to the South Atlantic anomaly. Basically, it refers to a 3 million square mile region where the magnetic field is weaker. That's where it is. And lately, radiation is not very effective in the higher altitudes of the atmosphere yet, but satellites orbiting over this region have been damaged beyond repair. In fact, the Hubble Space Telescope shuts down all of its instruments when it orbits this region in order so that it can be protected. We know about the effects that radiation can have on humans when it penetrates the magnetic field, because some astronauts have suffered some sort of eye cataract about 5 years after their space mission. 39 in fact. Apollo 11 has on records that there were some moments where they experienced a lack of, they experienced radio interference. During this time, the astronauts on the moon, and Neil Armstrong and Buzz Aldrin, said that they could see flashes of light even with their eyes closed. This was radiation penetrating the magnetosphere, and astronauts had suffered eye cataracts from this. Why is this happening? The big question. Some believe that, so I mentioned that the geomagnetic field is created by a dynamo effect from within the core. Some believe that the core is cooling, solidifying, and so this is limiting the thermal movement, hence it's diminishing. But not many are supporting this idea, because computer models have shown that the polarity in that region has reversed. It is different from its surrounding area. We are familiar with this because we saw the model, and we know at certain instances there are times where this is just one instance, I mean there are times where a certain area would have a polarity different from that of its surrounding region. So could the South Atlantic anomaly mean that the magnetic reversal is underway? That is exactly what scientists think it is. The last pole reversal happened 700,000 years ago. We might be due for another one. Effects of such an event. The first to feel these changes are animals who use the Earth's magnetic field to navigate. Mostly, an example are bats. In fact, studies have shown that when a bat is subjected to an external magnetic field, which interferes with its internal compass, the bat disorients itself. And we know that bats do follow the Earth's magnetic field to navigate. Whales are also another animal that uses the magnetic field. In fact, scientists were able to find a correlation between whale beachings and magnetic field anomalies. In fact, many migrating animals, also birds and turtles, who use the Earth's magnetic field. In terms of humans, a weaker field might cause cancer, in the sense that we know that exposure to certain radiation does mutate DNA within cells and can lead to cancer. So, at this stage there is not much that we can do. There is no way that we can stop a magnetic field reversal, we can only predict it. In 2010, the European Space Agency launched SWARM. It's basically a system of 3 satellites. One orbits the Earth at 500 kilometers, the other 2 at 400 kilometers. Their job is to scan the globe for defects in the magnetic field. They assume polar orbits, they orbit around the poles, and with this type of orbit they are able to scan all of the globe in just a few amount of revolutions. They have very, very minute and sensitive equipment. They can detect the slightest weakening in magnitude and even reversal within the magnetic field itself. We only hope that they can advance us. They can tell us well in advance about weakenings in magnetic field, so we can use them as a planning tool in the future. If there are no questions, that is all from my part.